What is linearization? Linearization is where you take a curve, like x squared, and you turn it into a line.
My dad's strong!
You got it.
Here we have a pretty clear distance versus time graph where if you've been studying your flashcards from the previous section, you would know that this is a y is proportional to x squared. So to linearize our data, we can always go back and view data here, but I happen to already have it pulled up with some of the important information shown. If I want to get rid of a column in Plotly, you right click inside of the graph and remove selected column. All right, so this is our x and this is our y. We want to make an x squared column. So what we do is we go into formulas and we're going to choose this as our x. We don't need a y. And just do x squared. Run the fit. Now, when we plot it, remember, we still want this to be our x-axis. So what was our x variable? It was time. So let's go ahead and rename this as time squared. We'll take a look at why this is important in the bonus features in, I guess, the part 4 that I'm going to make, where we analyze slopes and areas and units. So here we have time squared, and we're going to create a scatter plot with time squared as our x and distance as our y. By doing so, we've created a new plot, and it looks very linear. This is obviously made up data, so we would expect a pretty good fit. Add fit to this trace, linear, run the fit, and add the results to your plot. All right, so now y is equal to x. Let's modify this. I picked a very simple one for us because I want to show you how to clean up your equation. Y is not what we want. We want distance in there. So we look for the y and we write d. Whether it's a displacement or a distance time graph, that's up to you and your professor, and what variables you choose to use are up to you and your professor. Time, and then I'm going to actually go ahead and use a little bit of code here, sup2/sup. There. So now we have distance is equal to 1 times time squared. Let's look at another more exciting example where there's some more coefficients and it's a little bit more complicated to create that fit. So what we've done is we took a curve and we've linearized it. So add yourself a fit. Looking at this particular graph, I can't tell if it's inverse or inverse squared. So we're going to try a couple of things. First thing I'm going to do is create, well, I guess it says inverse squared, but let's just rename this as mystery data. All right, so I'm going to create a new column here. I'm going to create a column where y equals 1 over x. And then we'll create that column. And then we'll try another one where we create 1 over x squared. And find out which one gives us a better linear fit. I'm going to duplicate this because I want another x value and another y value on the same graph. We're going to plot these data points, and they're both going to look, okay, one of these will have a better fit than the other. So I'm going to fit the data, mystery data, 1, add fit, linear. All right, and we get a value of 1.00. So that's good to know. That's probably the one that I'm going to use. But let's just cover our bases and make sure the other one didn't do exactly a 1.00 fit, which it doesn't. It gives us a 0.85. So The blue data here was the 1 over x squared, and the orange data was 1 over x. So because the blue data had a better r squared value, we're going to choose that and decide that the best model is the inverse square. Thanks for watching, and I look forward to feedback. Professors or teachers can email me at dan@plotly, and we can do some Skype training or Google Chats. I can also drive to certain schools or fly out for certain regional events. If you have general feedback about my videos or about my website, check it out at mrpfeiffer.com, and I look forward to hearing from you guys again. Thanks.